This video is how to create a global dimmer for a matrix style fixture in Unreal 5. I had a client ask me about this, so I thought it was a good opportunity to show how modulators work. So in order to do this, I have two fixtures that I'm kind of going to demonstrate with. One is the case where we have a global dimmer and then each cell has a red, green, blue, and dimmer. And the other case is a global dimmer and each cell just has red, green, blue. I've arranged them both in kind of a 4x1 style, and then I'm applying an input modulator to them in order to kind of do the heavy lifting here. Now, if you don't know what an input modulator or DMX modulator is, if you go to Blueprint class and you search for modulator, it should be the only thing that comes up. You can create a DMX modulator here. It'll just kind of create it as a Blueprint class. If I open it up, there's nothing in it by default, and what I'm going to do is I'm going to override either the modulate or modulate matrix. So it depends on if you're using a matrix fixture or not. So in this case, it is a matrix, so this is what I'm going to use. This is the values of the cells coming in, and this is what I'm going to send out. I've already done this once, so I'm not going to recreate it from scratch, but I'll go through what I did. So then in order to kind of, what most people I feel like try to do is just add a dimmer component to this, but unfortunately the way the system's set up now, it doesn't understand what to do with it. There is a dimmer value here, but it's being used per cell and not in a global fashion. To send DMX, I have my Magic Q PC running over here, and to simulate this fixture I have my global dimmer and then my 4 cells, and then a global dimmer and my 4 cells for both the types. So what I'm going to do first is show kind of how it works on the one that has a dimmer per cell, and then we can kind of go from there and show the other example. So first thing I'm going to do is get the matrix cell values, set that as a local variable. Then I'm going to get all the normalized values for the fixture itself. So this is going to query everything that's not inside of a matrix cell. I'm going to get the dimmer channel, store that as a variable. Then I'm going to use the cell values and go through them and find the dimmer value in each cell. So I'm using a for loop. For each loop, storing the cell map as a variable, finding the dimmer, multiplying the dimmer by the main dimmer that we got earlier, and then I'm adding it back to itself. So I'm going to use this add node. It will overwrite it if it's already there, and if it's not there, it would add it. So we're just kind of overwriting it in place. Then we're going to set it back into the original array. So we're using that, we're using the index, and then we're creating this normalized attribute map with the cell map and setting it back. And then on the return node, we just pass in the cell values. So in order to kind of demonstrate this, I'll bring over the magic cube. And so the one on the left, so if I set the individual cells to full, and then I set the main dimmer and kind of bring it up and down, we can see it's working as expected. I could also set the cells to different colors and go back to the dimmer and bring it up and down, and I'm going to get the same result, right? So this is great. The only kind of caveat here, and I don't remember how lights actually deal with this, but if I bring up the main dimmer and the cells are at 0, nothing happens, right? Because you're just multiplying 100 times 0. So I think that sounds about what I remember, but that's just for that use case, right? So the other possibility is that we have a matrix that has a global dimmer and no individual dimmers, but just RGB cells, right? So basically we're going to do the same exact thing in the beginning, but once we get to the other portion of it inside the cells, instead of just finding the dimmer, I actually have to find red, green, and blue individually. I'm going to multiply them times the main dimmer value, since it's proportional, right? And then add them back in, and we're doing the identical thing. Other than that, we're just looking for 3 values and multiplying instead of a single value. And to demonstrate that, if I bring this back over, same thing. If we set the lights to, say, white, and I bring up the main global dimmer here, I get the effect I'm looking for, and it would work the same way, right? So if I went through these and said red, green, blue, white, right? And then kind of brought it up and down, I'm going to get the same kind of idea. And this is kind of just one handy way that you can use modulators to get some work done for you. There are some built-in ones already, so you apply them here on the fixture. So if you actually look, we have ones to convert CMY to RGB. There's one to add delays if you want. You can do extra cell attributes and things like this for pixel mapping. So it's really kind of clever what you can do with this without having to dig into C++, because the other option if you wanted to do this is actually you would have to go and edit the fixture itself. So if I open up the fixture and look at what's happening inside of it, this push matrix cell data is what's doing all of the heavy lifting. So inside of this, what it's actually doing is going into each component, looking for these values, and then pushing them into the cells. So you actually have to open this up in Visual Studio, go to the section where you're looking for dimmer, and kind of do some stuff in there. The important thing to note if you try this method is that it uses these lookup names. It doesn't use the component names, so you can't have two things named dimmer or you're going to run into some trouble. So on your fixture type itself, the one that's outside, maybe you'd call it global dimmer or something else so that you can differentiate between the two. But that should cover kind of the easy way to do it with modulators and give a little intro into how those work. And hopefully we'll do some more of these for some other advanced topics.